Ladies and gentlemen, we have detected gravitational waves. We did it.
The announcement of the first detection of gravitational waves, hailed as one of the biggest discoveries in the history of space science. So what's all the fuss? Just what are gravitational waves and what can they tell us? Why is detecting gravitational waves such an incredible scientific and engineering achievement? Join us as the National Science Foundation answers these questions and more in Einstein's Messengers, an award-winning documentary produced before the detection that explains the opening of this whole new window on the universe. Einstein's Messengers is coming up next.
into the darkness to read the messages written on the night sky. Since Galileo first turned a telescope to the heavens, astronomers have probed the planets, the stars, the distant galaxies. But there are some mysteries so deep, the answers cannot be found with traditional tools. For those, it takes something entirely different. A revolutionary new kind of observatory. It's not a telescope. It's something far more radical. Built to detect a whisper of a signal that's never been directly measured. Known as LIGO, it is 20 years in planning, a dozen more in construction, and it all comes down to this moment, the moment LIGO begins searching the cosmos, on the hunt for a whole new kind of cosmic messenger.
Let's begin.
Professor Ray Weiss has been dreaming about this moment for decades. Weiss and his colleagues had long been convinced there was another way to study the universe, beyond traditional telescopes.
When you start looking with other ways of looking at the image, this thing that it looks so pristine and pretty at night and so placid puts you into a good mood about coming to peace with the world. If you really look a little harder, you'll find out there's all chaos going on.
Chaos. From the fiery collision of neutron stars to the eruption of a supernova. Weiss believes these cataclysmic events leave behind clues about the fundamental nature of matter and energy, even the origins of time and space. These clues are what LIGO measures. They're called gravitational waves, and they're not anything like the gravity you thought you knew. It was Newton and his apple that first defined gravity, the force that pulls the fruit down, the force that pulls the Earth into orbit around the sun and holds it there. But Albert Einstein redefined all that in his famous general theory of relativity. Gravity, he said, isn't the attraction of objects like stars and planets. It's a distortion of space and time, what Einstein called space-time.
What general relativity tells us is that space is not a simple, flat arena in which matter and energy plays around, but itself can be dynamic. It can change its shape. It can curve.
According to Einstein, space-time is like a fabric, and what we call gravity is the warping of this fabric by a massive object, like a star. A planet orbits a star when it's caught in this warped space, like a ball spinning around a roulette wheel.
So it's not that there's a force between them, it's that the space where they live is creating these holes and they're falling into each other's holes.
It's an astonishing idea, and it led Einstein to a prediction that when a massive object collides with another, or changes speed or direction, it produces waves in the fabric of space-time. Gravity waves. Like ripples on a pond, these waves travel outward from their source, carrying information about the events that cause them. Racing at the speed of light, they are the ultimate cosmic messengers. Einstein's messengers.
The gravity waves just permeate, they go right through everything. The universe is totally transparent to gravity waves. Now think of such a thing. What that means is that if you get a gravity wave, it hasn't been messed around with. And you get what exactly happened at the source.
As scientists tried to simulate these waves, they found that up close, near violent events, they can be immensely powerful. A passing wave causes objects in its path to stretch and compress. Stretch and compress.
And if you're in a place where the gravitational waves are very strong, like near a black hole, they could tear you up. They could stretch you to pieces. In one direction, squish you the other way. You would be very upset by a strong gravitational wave.
But by the time they reach us, they are nowhere near as strong.
Just as the waves on the surface of a pond get weaker and weaker the farther they propagate, so do gravitational waves, which is why they're so weak by the time they reach the Earth.
Just how weak are they? After traveling across the universe, the average ripple would stretch a yardstick by only a tiny fraction of the width of an atom.
It's a number that is so small. Einstein saw that number in the 1916 paper and he said, this is just too small to deal with. Nobody will ever measure such a thing.
The prospect was so daunting, it took more than 40 years before a scientist decided to try. His name was Joseph Weber. Weber developed the first real experiment to detect gravity waves, a vibrating cylinder. A clever idea, and although Weber's detector wasn't sensitive enough to measure gravity waves, the excitement surrounding the experiment motivated many. Ray Weiss, a young professor at the time, thought he had a better way. The key to Ray's idea lies in the way a gravity wave distorts the fabric of space.
This is what happens to space itself. It stretches in one direction and it compresses the other. It collapses up and down and it stretches sideways. Here's a gravity wave at a certain frequency. The frequency is once a second or something like that. That's what it does.
To measure this stretching and squeezing, Ray turned to a device called an interferometer. A laser beam is split and sent down a pair of long perpendicular tubes, each precisely the same length. The two beams bounce off mirrors and recombine back at the base. The light waves come back lined up in such a way that they cancel each other out.
When you add them together, you get nothing. You get a zero, big fat zero. No light gets detected in the photo detector.
But when a gravity wave comes along, it distorts space and changes the distance between the mirrors. One arm becomes a little longer, the other a little shorter. An instant later, they switch. This back and forth stretching and squeezing happens over and over until the wave is passed. As the distances change, so does the alignment between the peaks and valleys of the two returning light waves. And the light waves no longer cancel each other out when added together in the recombined beam. Now some light does reach the detector, with an intensity that varies as the distance between the mirrors varies. Measure that intensity, and you're measuring gravity waves.
The light takes a longer time in here than it did in this arm. Now it takes a shorter time, and these things don't cancel so beautifully anymore. And that is, in fact, the whole idea.
By 1990, labs had begun to spring up across the world with the goal of finding ways to measure tiny gravitational waves with an interferometer.
I guess that's looking better.
It's a big challenge. In some sense, you could describe it as a high-risk experiment. Oh, but the payoff is enormous, and that's the thing that keeps you really motivated.
Now, at Twin Labs, in the heart of Louisiana, and in the high desert of Washington State, dedicated teams of scientists and engineers are undertaking one of the great technological challenges of the new century.
We are measuring distances that are almost unthinkably small. These small effects are coming from these big masses far away, from black holes, from neutron stars, and that we are going to see things happening in the universe by measuring these small things.
It's called LIGO, short for Laser Interferometer Gravitational Wave Observatory. Each LIGO lab is a real-world version of the interferometer Weiss envisioned, made up of two arms, extending 4 kilometers in length. The size is key because the tiny stretching and squeezing effect increases in proportion to the length of the interferometer. The longer you make it, the more the mirrors move, and the easier the signal is to detect. Also key is state-of-the-art optical and laser technology. Mirrors, polished to a precision never before attempted. High-powered lasers, among the most stable in the world. LIGO is the work of hundreds of scientists, engineers, and students. The LIGO Scientific Collaboration, based at the labs and at dozens of universities around the world. Their goal? To measure the movement of mirrors down to 1,000th the diameter of a proton.
That's something no one has ever done before. It's something that requires pushing the limits of technology in every sense. And what usually limits you when you're trying to measure something better than ever before is noise.
What physicists call noise is a host of vibrations and other disturbances that can shake the mirrors and mess up the data. Welcome to the modern world. LIGO scientists have always known that to detect a gravity wave from space, they'd have to isolate the signal from the noise on Earth. The challenge is like trying to make out a tune from across a busy city. You need to know what you're listening for, and you have to separate it from all the surrounding noises. That's not so easy. The LIGO labs were built in quiet, rural areas, but their instruments are incredibly sensitive. If a tree falls in the forest, they hear it. LIGO's Louisiana site is surrounded by logging, but that's just the beginning. Even waves thousands of miles away can affect LIGO's instruments. Then there are the earthquakes, windstorms, volcanoes. The whole planet is shaking and vibrating.
Everything else on our planet wants to move the mirror more than the gravitational wave does. So the big challenge is, how do you keep a mirror so still against all of these other external forces that are trying to push on it, so that it'll only move when the gravitational wave comes by?
The answer begins with one of the largest vacuums ever made. A laser beam can travel down LIGO's long arms without the distorting effects of air, and remain stable as it bounces back and forth between mirrors. The mirrors themselves are cushioned with a suspension system that cuts outside noise by a factor of 10 billion. Springs and weights absorb movement from the ground. Vibrations are further reduced by fine wires that suspend the mirrors. If any remaining vibrations get through, a series of tiny magnets nudges the mirrors just enough to exactly counter them. The ultimate goal is to approach the very limits of measurement, down to a scale so small that quantum laws turn the straight lines of a ruler into a tangle of fuzzy impressions. Even with noise reduced to the lowest possible level, LIGO must still be able to tell when an incoming signal really is a gravity wave. That's one reason 2 identical labs were built, separated by 1,900 miles. If both labs pick up the same signal, chances are it's not noise from Earth, but a gravitational wave from space. Once detected, these waves can be electronically converted to sounds. Sounds you can hear. Take neutron stars in the act of merging.
They make this wonderful chirp. It's a cosmic chirp.
And it would sound something like whoop.
It goes whoop, like that. Whoop.
And that combination of the observations that we make together with numerical simulations, I expect, will revolutionize our understanding of general relativity and its consequences.
If the team can track down these titanic explosions, they can go after the biggest explosion of them all. LIGO holds this amazing potential to go back to the beginning to the first moments of space and time. The Big Bang.
Takes you all the way back to the instant of creation. Now imagine such a concept. Now, nobody's guaranteeing us that we will see something from that. But gravity waves are the only way you will get information from the air. That alone is a justification for doing everything you can to try to detect them.
The hope is this new science will take physics even beyond Einstein's great theory, and one day yield discoveries about space and time as fundamental as the discovery of the atom.
Most of what we know about the universe comes from electromagnetic radiation. LIGO as a concept is important because it's going to potentially open up a new window on the universe.
As the search for gravity waves begins, LIGO is inspiring kids and adults alike. Stargazers like these are actually becoming part of the action. Because the LIGO team needs such vast computing power, it's turning to homes with computers all across the country, tying them together in a vast network. Anyone who wants to help can join the search for gravitational waves through a project called Einstein at Home.
Gravity waves are rumbles in space that they're searching for. They look for them a lot.
From these ranks may well come the next generation of gravitational wave explorers.
I hope I never stop stepping back and looking at the big picture and saying, instead of trying to get this one piece of electronics to work, I'm trying to detect gravity waves. And that's something that, when you stop and you think about that, there's a moment of wonder there. You say to yourself, what on earth am I doing here? This is incredible.
I think that's what characterizes many scientists. They are people who never lost their childlike wonder about the universe, and they're still driven by that childlike wonder.
LIGO is now attempting to filter out the noise and pick up the symphony of space-time. To make out the tune in the cacophony, the melody that echoes across the universe.
And we're now on the verge of being able to listen to the music being played on the fabric of the universe, to what you might call Einstein's symphony. That's what LIGO and its sister projects are all about.
History has shown the great discoveries in science usually occur when revolutionary instruments provide new means to explore the universe. LIGO gives us a fresh set of eyes, an entirely new way to uncover the universe's deepest mysteries. Today, LIGO stands on the brink of discovery. A dream for decades, it's now a reality. A new branch of science, just being born. An observatory unlike any other, ready to hear the music of the cosmos, echoing from the most distant reaches of space and time.
Because you see, if I had messed up somehow,
Oh, yeah, okay, I see.
And I-
So you made a,
if I made a ground, that could have done you a job.
okay. You wouldn't do that.
Well, of course I could. You know, yeah, it's
Well, hello everybody. This is Scott Roberts from Explore Scientific, and this is the OpenGOTO community, our 113th episode. And with me today is Tyler's chair, Tyler Bowman's chair. He must have run off to take care of a customer. We've got Jerry Hubbell with us and Kent Martz. So we've got, it's great to come back and see you guys. We had a really amazing weekend with Friday's Mount Wilson live event. That was the second time only they've done any kind of live broadcasting from Mount Wilson Observatory. We got treated with live views through the 60-inch telescope, so that was really cool. On Saturday, we had the Astronomical League, and it was the theme was the shaking universe. And one of their plenary speakers was Dr. Shane Larson, and he's with LIGO and heading up the LISA project, which will put basically a LIGO instrument in space, orbiting around Earth. And so I thought that was spectacular as well. He was a great speaker, a lot of charisma, and was able to translate some pretty complex concepts into everyday language. So that was awesome. Gravity wave research, it will change the science of astronomy again and again as they make new breakthroughs. So that's very cool. While we're waiting for Tyler to come back, let's jump over to Jerry Hubbell. Jerry's got his next install of the Mentor program, which we've been doing. Jerry, how you doing, man?
Good. I didn't realize I was just preparing, getting my charts. I'm going to be talking about celestial charts today. I was getting some of that ready, but I'm pretty much ready to go.
Are you all set to go?
Yeah. Let me that's pretty much what the topic is going to be. I'm going to move my Zoom window over to my other screen. That's why I'm looking sideways, because I'm looking at myself and you guys. But when I'm looking at my documents, I'm looking at everybody.
Yes.
So I'm talking to you. I'm talking to the camera. So let me go ahead and share my screen.
Okay.
Let's see. Screen one. All right. So I also wanted to talk about this is from the document I created for training, our mentor training. If you're new to this, you haven't seen any of our previous episodes where I started talking about the mentor training, and Scott's talked about it. Basically, I've created this training documents for our staff. We have training every Friday, or pretty much every Friday, and it's just a general document. But last time I gave a talk, well, on, I guess it was last, what was it? It wasn't Friday, it was Wednesday, I guess. I told everybody that everybody kept asking about how can I get this document and where can I get this document? And it's a draft document, okay? It's our PMC8, it's part of our PMC8 training program. It basically starts off from scratch, describing, starting with the celestial sphere, and then going on from there and talking about some all the terms and all the topics that are involved with what you need to learn to use a go-to mount. Really, is what it comes down to. It gets you prepared to use a go-to mount. So if you look at our previous episodes, the last 2 or 3 episodes, I think this is our 3rd or 4th one now talking about this stuff. Is that right, Scott?
Yeah.
So to make a long story short, I had a request last week about where can I get some of this information, and I got talked into posting the draft version of this document.
Mm-hmm.
And as you can see on the screen, it says draft version 0.6, 4th of August.
Oh, yeah, you weren't quite ready to release it, but
right, and it hasn't been updated for a while. It's not even feature complete. It's not even complete yet. But I posted it on the forum. So if you go to the files section, actually, if you you're a member of the PMC8 forum, you would have got an email today saying it was posted. And I can actually show people where it's at. Let's see here. This is kind of a preview. All right, so if you get on the forum, why is it not? It's under the main group. So if you go to the menu items on the left, you go under files, or scientific official files. Can you see that? Let me zoom up on the.
It's very tiny.
Yeah, I'm gonna make it bigger here.
There we go.
Is that better?
Yeah.
So if you start out on the main group, all right, and you go to the menu on the side, you go to files, or scientific official files, right? You'll find it right here. You scroll down to near the bottom or over halfway. You'll see ESPMC8 training program draft version, September 4th. And you bring it up, and that's what I've already got loaded. So I'm gonna ditch this one and go back to my other document. So that's this document here. And so that's for everybody that was asking for the document. So I don't know, you want to real quick see who's online right now with us before I get started?
Sure. We have Stefan Delpra who's saying good morning to everybody. Dale Beasley, good afternoon. So we got good morning and good afternoon at the same time. Michael Whitaker, good evening, everybody. I love this, because you don't know where everyone else in the world is, but it's cool. It's global, folks. Bergman Scooter says hello. Marco Polo's watching. Pekka Hatola says hello, everyone, from Stockholm, Sweden. Michael Whitaker says Jerry's presentations are priceless.
Oh, thank you.
Yep. Conrad Sanders says hello from Minnesota. Aaron Thompson liked our programs over the weekend. Thank you very much. Stefan Delpra says the observatory on the weekend was amazing. Yeah, it was really cool. What happened though during the weekend, I broadcast this and I was told, this happens to me sometimes. I get a video program and I go through, what I think is due diligence to get permission to use it. Mount Wilson Observatory has allowed me to use the video that had Claire de Lune and some music behind it. Well, it turns out that Sony didn't like that, so so they stopped the video from being shown. They said in 243 countries. So I am re-editing the video, okay, so that I will take out their music, but I am going to keep the piece that has Edwin Hubble live in there. Well, the film of Edwin Hubble, and also Milton Humison, because those two guys were the ones that were largely responsible for getting us the data that we need to know, that the Andromeda Galaxy was an external galaxy, and it was Hubble's science papers about the expansion of the universe and the Hubble constant that we still use today to try to measure the size of the universe. Who else do we have here? Mentioned Dale Beasley. Clear Light 58 is with us. Kim Hay from Ontario, Canada. Hello, Kim. We've got comments here. Clear Light 58. I did recommend that if you guys are interested in participating in the December 21st Star Party, to get in touch with me. because that's when the great conjunction is going to happen between Saturn and Jupiter. Clearlight 58 said he's practicing and working right now, trying to be able to go live on the 21st. I have a good view to the southwest at dusk, so I have to get some of my gear to work and hope for good weather. I would recommend to anybody that's going to do this is to try to lock in on Jupiter during the daytime. If you think that might be daunting, and then what you could do is get on Jupiter the night before with your telescope all polar aligned, and just bag the telescope and then turn it on, and you should have Jupiter pretty easily. You want to have it to where you can still see, you got Jupiter positioned so that Saturn should be in the field of view at the same time. And long before it gets really dark, you should be able to see Jupiter and Saturn. So you would have more imaging time, as it starts to set. So I think that's a good strategy. Let's see.
Right.
Conrad Sanders says, I think there's going to be a lot of used telescopes for sale when COVID-19 blows over. I don't think so. I think people don't typically, even after a giant mega event like the Mars opposition, Comet Hale-Bopp, lots of things like that, they don't just get them and then just dump them on the market. These people normally stay in the hobby and keep their scopes for another amazing event. So,
yeah, if you invest several $100s in a hobby, and you had enough interest to do this first event, right? You typically get hooked on stuff. You get with people. Of course, it's difficult with the COVID getting with people to do star parties, but that's why we have our global star parties. So people get excited, and you talk about it, and you plan, and you talk about equipment and the sky and everything else, and that's how you stay in the hobby, basically.
Yep. Yeah, and that's why the Astronomical League is now starting their monthly program. They're going live every month, and we're the ones broadcasting it for them. So we're real happy to be doing that with those guys. And what else here? We have actually quite a few people on.
Yeah, I just wanted to see. Hopefully, some of the people that have been on before that requested the document are going to download it and listen and find out about it today.
Right.
What we don't have a list of people named. I didn't get any emails from people asking for it, but I want to make sure I said something about posting this document at least, and maybe the word will get around. It's definitely everybody that's on the forum got a message from me saying it's posted. So,
right.
At least if you're on there already. And if you want this document and you're not a member, then please join the PMC8 forum.
Yeah, it's free to join, and there's tons of good information there.
Yep. And you don't even have to be a PMC8 owner. You can just be somebody that's interested in it, or just interested in what is
some of the information that's
some of the information and how people are using the system. And there's tons of information and pictures and things out there.
Right. Right.
All right. So let me get started. Celestial charts. That's the next section. So celestial charts or star charts are like charts that we use to navigate the Earth that depict surface features, and they have a coordinate system. And from the last couple of episodes, I talked about the coordinate system for the celestial sphere, which is the right ascension and declination, which is the same as basically the longitude and the latitude on the Earth's surface. And I wanted to show some examples of some charts, and I'm starting with the one that is in the center of magazines. It's kind of one step above a planetarium chart. And if everybody's seen planetariums, this is kind of what it looks like. Okay. And this is Sky and Telescope's interactive chart. They've really got a nice chart that's online. And you can I don't know if you can see the URL at the top. That's what it is.
Yeah, it's skyandtelescope.org/interactive-sky-chart. I guess I can
Right.
put that up there.
Mm-hmm. And then, so I'm going to put my zip code in here and see what it comes up with. Oh, okay. So it came up over here, Locust Grove, Virginia. That's where I'm at. And that's pretty much where I'm at. That's where the Mark Slater Remote Observatory is. So you can set the date and time also. So this is what the sky looks like right now for me. And if I'm facing north, I guess that's what this is. So I can scroll around. So you can see my cursor's moving
Oh,
around.
that's cool. Yeah.
Is my cursor big enough for everybody to see? I know I got complaints every once in a
It's
while
small,
about that.
but you know.
I can enlarge it. I think I can enlarge it even. I messed with this the other day thinking about it. So I'm going to type in mouse. Moused.
Moused.
Moused. So now I can say adjust mouse and cursor size. Okay, so now I can make it really big. Okay, how's that? Is that nice
Good.
and big?
No.
No? Okay.
No.
So let's see what facing south looks like, at the horizon. You can see on the left-hand side, that's kind of cool. It's got the charts in the sky. And you can see what's up. You can see what the direction to look at. And but this basically tells you what's up in the sky and where it's located. And the center of the chart is zenith, which is where this star is at. I don't know if it doesn't have a name for that star. Algol is right there. But that's Andromeda.
Right.
Right here.
Yeah.
Pegasus.
Great Square of Pegasus.
And there's Mars right there.
Mm-hmm.
So if I center on Mars, I don't know why it doesn't show Mars in the left-hand chart, but it shows it on the big chart. So that's plotted. And then I guess Jupiter and Saturn have set already. But that's just a basic star chart. It's like in the magazines. That give you some information. That's a good one to start with. The next charts that you can buy that are paper charts. Now I'm going to go back. I'm going to go back and forth between this electronic chart, which is a paper chart also. And you've got a planisphere there. Maybe you can show at some point here in a minute.
Oh yeah, I got my
but this is like a planisphere chart, is what this is. It's an all sky chart, basically, is what it is. So let's start with this is Sky and Telescope's Pocket Sky Atlas. This is kind of a one step above the.
Yeah, those are Wiltirian maps.
Right? Wiltirian maps, right? And this looks very similar to our packaging because that's what we use. He's created these charts, a version of them for us to use in our packaging. But one of the things this shows you is it's got the two axes, which is different from that all sky chart. It's got our right ascension coordinates, which is along the x-axis down here. You can see where my hand is. 1 hour, 16, 15, 14, 13 hours in right ascension. And then declination. This is in the southern hemisphere, so it's starts at -30, -40, -50. And one of the features of a paper chart is it's a Mercator. It's a conical projection, or sometimes they do Mercator projections also for larger ones, but I think this uses a basic conical projection. And what you'll see is that the area, as it comes to the pole, you can see it narrows down, the coordinates narrow down. So you see 16 hours and 15 hours. That's the distance in the sky as you look at it. It comes to a point at the north. It's just like the lines of longitude do on the Earth's surface. They come to a point at the poles. That's the same thing these charts will do. They come to a point. So you can see the difference between 15 and 16 hours at the top of the chart is a lot larger than it is at the bottom of the chart. That's because those lines are coming together. So if you know, for example, and then you got the curving lines of declination on the chart also. You can see the minus 50 degree line, the minus 40 degree line. And then if you want to, you have to interpolate the coordinates for like Eta Centaurus right here, this star right here, Eta. All right. You'd have to interpolate this by first on the declination, you can extend this, you can follow that parallel line down here to like right about here. Okay. That's like, let's see, it's like 10 divisions per, yeah. So each one of those divisions is 1 degree. So this is like minus 53 degrees. Eta is at minus 53 degrees dec, or somewhere right around there. And it's also the same way you extend this line of right ascension down, and you interpolate down here. So that's right around here. So that's going to be like 13 hours, and each one of these is 10 minutes. So 13 hours and 35 or 40 minutes, 35 minutes, 30 to 35 minutes. All right. So Eta is at 1335 hours and 53 degrees, minus 53 degrees declination. So that's how you would read the position of a star like that. Does that make sense?
Yeah.
You'll get used to that.
Makes sense to me.
Yeah, so that's what you have to do when you use charts and you want to know what the declination and right ascension is for a star. You have to interpolate. Now, there are tools available for bigger charts that come with an overlay that actually you can overlay the grid system on top of the chart, and it lets you look at and measure directly off the grid. Now, there's another chart that's part of the Pocket Sky Atlas. This is a higher resolution chart. You can see each square. Now, this is 5 degrees now, and 20 minutes of right ascension for each grid position. So now, and the other thing that I wanted to point out is that charts give you the stars in different diameters, different sizes, and that's based on the magnitude. So if everybody recalls, a first magnitude star is brighter than a 6th magnitude star. Okay, so the lower the number, the brighter the star. Okay, that's basically what it is in magnitude scale. And going from a 1st magnitude to a 6th magnitude scale is equal to a brightness ratio of 100. So 5 magnitudes of change is equal to 100 times the brightness. And it's a logarithmic scale. Okay. If everybody in high school remembers their log functions or exponential functions, basically, and that's based on how your eye responds to light. It's a logarithmic function. So, and that's the way charts are depicted. So you can go all the way, like this chart depicts magnitudes from 2nd magnitude, which is really big, with like the nebula over here on the right is a 2nd magnitude star. And down the smallest stars that are depicted are 9th magnitude stars. That's a key thing about stars too. So now, this is a paper chart. The next paper chart I'm going to show you is from a chart called Uranometria, which is published by Wilman Bell.
Mm-hmm.
And let me see here. This is a bigger scale. So that scale on the normal charts, this is
this was also done by Wilterian.
Wilterian, right? Mm-hmm. This was actually done in the 80s. This chart first came out, and I bought them then, and I bought another copy, and I probably got 3 copies of these charts. But the last ones that Wilman Bell put out there was 3 volumes, one in the northern hemisphere, one in the southern hemisphere, and then they had a catalog book that listed all the objects. They've combined all that into one star book now, and it's really a nice book of star charts. If you can get one, I would suggest if you're really serious into
Oh yeah, especially I
charts.
think is one of these publishing houses is closing.
Yeah, Wilman Bell
It
is
is
actually
Wilma
shut
Bell.
down. Yeah, exactly.
Yeah.
But
So
other distributors may have these in stock for you to
yeah,
get.
this is a classic
Yeah, this is
star
a
chart. If you're looking for
yes,
some of the best printed star charts available, definitely this would be one of the ones to be looking at.
right. This came out in 1987.
It's all Epic 2000.
That's the same year I bought my Meade LX200. I mean, the LX5, I mean, in 1987.
Oh, you got a nice set of star charts
So
to
I got
go.
these charts along with it. Yeah, I was
Yeah.
excited about getting all these neat books back
Yep.
then. So you can see that the scale here is a little smaller now. You get much higher resolution. It's four, so each division on the right ascension axis is now 4 minutes,
Mm-hmm.
and 4 minutes is equal to 1 degree. So basically, each square here is equal to 1 square degree. All right, which is about the same size as my camera field of view on the at the Mark Slade Remote Observatory. So it's pretty convenient to see what kind of area you cover with your camera if you got like a similar thing. This book does come with a series of overlays so that you can interpolate between the major grid lines also. Um, this chart goes down to almost 10th magnitude. Um, and you can see down here at the bottom how small that star is, that little depiction of the star, that little dot. That's a 9.7th magnitude, and it's got a huge number of stars in the catalog in this chart. I mean, one of the other things I wanted to point out, which I didn't do on the let me go back to the other pocket star list. You've got a thing called the chart legend, which not only includes the star chart, the star magnitudes, but also all the different objects that are in the sky. How they're depicted in black and white or color, and the symbols for them. This symbology is fairly standard, I think, across star charts. Don't you think so, Scott?
Oh yeah. Mm-hmm.
So you'll see these same symbols for like for a double star. It's got a line drawn through it. Variable stars or a dot with the circle showing the different sizes or the different magnitudes of the variable star. Galaxies are drawn as ovals to show the size, and then the position angle is drawn, I think, on the charts for the most part.
Mm-hmm.
Star clusters and globular clusters have these symbols, and they're to scale typically, and also nebulae are drawn however they're drawn. You know, it's that's an example. But if you look at, I don't know why I was thinking at my menu thing at the top, my doesn't go away on me. Why won't it go away? I'm stuck. I can't get to the. All right. So here's this Virgo galaxy cluster. You can see all the different galaxies there.
I think it's fun to look at these star maps
Well,
because
they are. It's
you
really
know,
cool to just navigate the sky and just go across the sky and look at different
right?
charts and just see what's out there, just to get a good idea of what's up. So
Right.
or what's out there. So your Anometria. Here's another. So here's the Christmas tree cluster in the Cone Nebula.
Right.
So you can see the nebula is drawn in its real shape, close to the shape that it's actually has. And
And what's cool about this is Will Tirian does that part by hand. All the
yes,
star placements are done by computer, okay? So you can get the best astrometry.
right,
But the nebulosities, the galaxy positions, all these things, these are done, those were done by hand. And you can imagine I mean, there's a ton of deep sky objects, especially in Uranometria, and that was quite an effort.
Yes.
So it's kind of a masterpiece kind of work, you know,
Here's a rosette.
right?
And then you got little notes, the different objects have notes on them. Some of these I think some of these notes were put in by hand also.
I'm sure.
And then we've got this close-up chart, which goes all the way to greater than 11.5. You can see how small the stars are on there. So that's 5 magnitudes or almost 6 magnitudes dimmer than what you can see with your naked eye. So this is a great chart for telescope use. If you're star hopping, this is how you star hop. You go back and forth between a chart. So you go to this bright star, Satyr, right here in the middle. Okay, let's see, you're trying to go over a couple of degrees to another object. So like this right here, DO11. All right, let's say you want to see that. So you start out at this bright star and you need to go like 1.5 degrees over the center on this object. And you just star hop between, maybe you go up to these stars here. You go north and you say, oh, I see this grouping, right? And then
Right.
you go west or east a little bit and you say, oh, okay, I'm getting close. And then you can pick out these little asterisms. They're all called asterisms. So when you see these little 3, 5, 7 star little patterns, they're called
Yeah.
asterisms. And
Mhm.
that's what you look for from your chart into your eyepiece.
Mm-hmm.
So this gives you a good idea. So to navigate to an object, if you want to find out now, stars, fixed objects in the sky, we call the fixed objects. They're outside the solar system, basically. They have uh, basically a fixed right ascension and declination. But the right ascension and declination slowly change. We talked about this last time because of precession. Okay, which means the Earth's pole position changes, and the coordinate system is based on the North Celestial Pole being 90 degrees. All right, and it's fixed. So if the pole moves across the sky, then that means the position of the stars in terms of the coordinates are going to change over time. And that's why we have a thing called an epoch. All right, these catalogs that we're using today are referenced to January 1st, 2000. Okay. That's why you see atlases like called Sky Atlas 2000, because that's the reference time for the chart. So these charts show, like for example, this object here, the DO11 we were looking at. The coordinates that you look up on the chart here are the Epoch 2000 coordinates. All right. That's going to be different than the current right ascension and declination, which when you use a GOTO system, your coordinates that you're going to read on the GOTO system are going to be the current coordinates, not the J2000 coordinates. Now, these coordinates are very helpful though when you do astrophotography, because when you do something called plate solving and you plate solve to a reference catalog your image and it identifies where the center of your image is, it's going to reference that to the J2000 or the 2000 epoch, just like the charts are. So any coordinate you see an object on your image and you plate solved it and you move your cursor to that object, it's going to give you coordinates based on the year 2000. So that means you could go to one of these paper charts and say, okay, I know where it is. It's right here in relation to the stars. My dogs are going nuts again. Oh, I can't.
Maybe they detected a gravity wave.
Yeah, gravity wave.
Yeah, my dog barks at gravity waves. In fact, I'm going to get a bumper sticker for my car that says I brake for gravity waves.
Or you surf on gravity wave.
Surf the gravity wave.
So, so that's that in terms of paper charts.
Yeah.
Now, let's go to one more thing. Let me go back to the training thing. See if I've talked about everything here. I talked about the precession of the equinoxes, longitude, the right ascension declination axis, and I'm going to bring up one other electronic chart. Now, people today want to use electronic charts for just about everything. You don't necessarily have to use paper charts at all. And I use one called Carte de Seal. Other people use another popular one is called Stellarium. I just prefer Carte de Seal for various reasons. But let me bring it up here real quick. Hopefully it'll pop up nicely. I don't know why this. I have to pop up. Okay, so there's the chart. Can you see it?
Yeah. Looks
It
nice.
basically looks the same as it's got a dark sky, not a white sky. It's an inverted. But you can see, for example, it's got this is depicting the Milky Way. This broad brush of lighter color across the darker sky.
Mm-hmm.
I'm going to zoom out. So you can zoom out and see the whole sky, basically like the planetarium depiction, or like that first chart depicted I showed you, which is kind of nice.
Mm-hmm.
You can also, this is called the Altaz coordinate system. It's altitude and azimuth. It's not right ascension declination. You can see here, right? You can't really see the cursor probably very well, but that's south, and then on the opposite side is north. Okay. Now there's another depiction which is called the equatorial coordinate system, which does show right ascension and declination. All right, so this is the whole sky, and you can see how the lines curve around. The North Star is right here. All right, right here. Oh, it does do a big finger. All right, so you can see that, but you can also zoom up on the location wherever you want to center it. So I'm going to right click on here and center on this object. Okay. Then you can zoom in, and it brings in more stars. As you zoom in, it brings in more and more stars. All right. I don't think I'm mapped to my big star database. But you can click on the stars and it'll give you the information on it. So let's go to this one, like this one here, 63F02 Cygni, and you can get information about it. Okay. You can see the magnitude, the declination, and the I'm sorry, down here is the apparent right ascension declination. Okay. And then you got the J2000 right ascension declination, which is what you use when you're looking at a chart. Okay. So you get all kinds of nice information. And the other thing is it draws these nice circles on here for you to target. And then it's also got a rectangle for your camera view. You've got different ways of configuring the system. Let me look at something real quick. It should be using this catalog, but apparently I don't have it set up. Let's see if we can. Oh, it's mapped to F drive. I think it's actually on my M drive. See if it'll bring up these stars. Okay. Oh, see them pop up?
Yep.
Now see how they're all there now? All these, that millions of stars I've got in this database. Look how so this has got more stars than that catalog. This goes down to magnitude 18. Let's see what this star is. This is a magnitude 15th magnitude star right here. The one I've got highlighted, this UCAC. Where's the finger at? There it is. That star is magnitude 15.5. Okay. And it's got the precise location within the catalog. So this is really nice when you're doing photographs, and you absolutely can see all these stars in a photograph easily down to 17th, 18th magnitude when you're doing a 1 minute exposure on most telescopes. And down here at the bottom, it's kind of small. You can see the right ascension. All right. This is 30 seconds of right ascension. That's how zoomed in we are. So let me back out. So that's, let me zoom out to where it's a decent scale. Okay, so this is 21 hours and 20 minutes of right ascension, this line right here. And then the next line is 21 hours and 18 minutes. Okay, so that's 2 minutes of right ascension, and on the vertical axis is declination, and you can see that it goes from 43 degrees 30 minutes to 44 degrees. So this is 30 minutes of arc, or half a degree. So the field of view on this thing is basically a half a degree field of view in each box. All right, so this and I don't have this box set up for the MSRO, but you can see this camera covers about a half a degree by a half a degree field of view, is what this size is right now. So that's an electronic chart. That's what it's like, and you can zoom in and zoom all the way out. Like I said, it's kind of nice, and you can change the coordinate system from equatorial to altitude azimuth. And the nice thing here is, now let's say you're looking for, right now you're looking for you've got your DOB set up, okay, and you're looking for M39 to look in your DOB, okay, and from that, let me see, let's show, here it is. So right here you can see it's got azimuth and altitude values, okay. That's the current altitude and azimuth. Now it's going to change over time, so you can go to the chart and say, okay, where is it at, altitude and azimuth, and then you can go to your DOB if you've got a level on it, you know, any kind of scales on it to let you measure the altitude and azimuth of where it's pointing. Then you can just go near to that 310 degrees and 71 degrees altitude, 310 degrees azimuth, and start looking in there, and you'll find M39.
Mm-hmm.
That's how you would use the chart to find the coordinates.
That's great.
All right, so
Well, Jerry, thank you. Thank you for wrapping that up. We have an internal meeting that's going to be happening here pretty soon, so we will have to wrap up this program. I've got Kent Martz on with us. I know that Kent will not be on his regular program tomorrow because of our we have Alan Stern coming on at 3:30. But I like to do a coming attractions program, and certainly we can have Kent update us on what's going on with product, because we are getting we're getting down to the wire for holiday, and so if there's something special you're looking for, Kent can give us some idea on what's still available left to pick from our inventory at this time. You were saying?
Hang on.
Oh, okay.
There we go. Did you unmute me? I had so many screens open I couldn't find
Oh
my
no,
screen.
you were already unmuted. You're
Okay.
already unmuted.
Couldn't find my screen to find out if I was muted or not. So it's been hectic. We worked all weekend, packaging stuff and labeling stuff, and it's all hands on deck to get stuff done. It's been an impressive effort. One woman was labeling. She had done, when I was back there, she'd done 50 pallets. They're stacked up, and she has to put them on the ends. And she had labeled 50 pallets by herself. Those 50 pallets will be out of here tomorrow morning, and probably replaced by more pallets coming in as well. So,
What's the current look? What's it look like for shipping now? FedEx and UPS or whoever we go with. How does that look now for getting things on time?
The problem we face right now is that they send a truck and they take what we can get on the truck. And, it's like, can we duct tape it to the outside of the truck? Beverly Hillbillies sort of
put it on top,
strap it on, put it in the cab with the driver. So there's been days that the truck showed up and we put on what we could. And multiple trucks have been here, and we said we've got more, and they sent a rent truck and we pack it, and there's more. So that's the sheer volume that we are capable of processing has been exceeded at times in the last week or so. But then that is the capacity that the shippers have is also being stretched pretty thin, and scheduling trucks can be a challenge. If we have less than truckloads going somewhere, it can be quite the challenge to get a truck here. So it's easier to say we've got pretty good stock levels on some First Light things. Basically, you can go on our website and tell what we have, and either buy it from us or go to your favorite vendor and use your vendor to purchase it, and that's perfectly fine. But we've of the 20 telescopes in the First Light series variety pack. I'm guessing that's how many are there. We have what's that going to be? 8 in stock.
Yeah.
So the First Light AR 127 1200 Mazo 1. So that's a 1200 millimeter focal length, 127 millimeter diameter on a nice solid Mazo 1 mount. We've got a decent number of those. The First Light, the smallest telescope we have, excuse me, is the AR 80-900. So it's an 80 millimeter in diameter, 900 millimeter on an EQ3. Solid little scope. Be good for planets and the moon because it's got a long focal length. It'd be good on the moon. Got decent stock of those. That one, not even going to talk about the show.
Right.
Go ahead, Scott.
Well, we should wrap. We should.
Oh, you got to go. Okay.
We have to go. I'm sorry.
So,
but
buy your telescopes. Buy them now. Get your order in, or you're not going to get one.
Right. Check out your dealers or check us out and get what it is that you're after. So anyhow, thanks for watching today. We'll be back with you tomorrow. Don't forget to watch for Alan Stern and the Star Party, the Global Star Party tomorrow night. So it's going to be a lot of fun. And we'll have David Levy, David Eicher, Libby and the Stars will be on. I know that Bob Denny's joining us. Jerry Hubbell will be joining us. I'm sure you'll see Tyler and Kent. So and more to come. So thanks for tuning in. Take care.
They just started coming in. It's like,
and now, folks, it's time to say goodnight. We sincerely appreciate your patronage and hope we've succeeded in bringing you an enjoyable evening of entertainment. Please drive home carefully and come back again soon. Good night.